Hello and welcome to my YouTube channel ChemWis. In this video we are going to learn how to find the oxidation number of an element in pure and combined states. The lecture has been divided into three parts. In the first part we will learn certain rules for calculating oxidation number. In the second part we will do some exercise, and in the last part we will discuss some exceptional examples. Let's start with the rules for calculating oxidation number. Rule number 1. The oxidation number of an element in uncombined state is 0. For example, inert gas elements helium, neon, argon, krypton in uncombined state exist in monoatomic form. Similarly, lithium, sodium, potassium, beryllium, magnesium, calcium, carbon, silicon also exist in monoatomic state in uncombined state. Hydrogen, nitrogen, oxygen, fluorine and chlorine exist in diatomic state. Oxygen also exists in triatomic state in the form of ozone. Phosphorus and sulfur exist in tetraatomic and octaatomic form respectively in uncombined state. According to the first rule, the oxidation number of all these elements in this uncombined state is 0. Rule number 2. This rule is related to the oxidation number of first A and second A group elements. According to this rule, the oxidation number of first A group elements in combined state is always +1, while that of second A group elements is always +2. We know that the elements in first A groups of periodic table are lithium, sodium, potassium, rubidium, cesium and francium. And the elements in second A group are beryllium, magnesium, calcium, strontium, barium and radium. According to the second rule, in combined state, the oxidation number of lithium to francium will always be +1, and that of beryllium to radium will be. Rule number 3. This rule is regarding oxidation state of hydrogen. Hydrogen can exhibit +1 and -1 oxidation states. +1 oxidation state is the general oxidation state of hydrogen. -1 oxidation state of hydrogen is found in metal hydrides like lithium hydride, sodium hydride, potassium hydride, magnesium hydrides, calcium hydrides, etc. Rule number 4. This rule is regarding oxidation number of oxygen in combined state. There are 5 oxidation states of oxygen: -2, -1, -half, +1 and +2. Among these oxidation states, -2 is the most common one. -1 oxidation state is found in peroxides like H2O2, Na2O2, etc. -half oxidation state is found in superoxides like KO2, RbO2, etc. +1 oxidation state is found in fluorine oxide, O2F2, and +2 oxidation state is found in oxygen fluoride, OF2. Rule number 5. Oxidation number of halogens in combined state. These elements belong to 7th A group of the periodic table. These are fluorine, chlorine, bromine and iodine. These elements have 7 electrons in the valence shell. Because of that, all the halogens show -1 oxidation state. Fluorine, being the most electronegative element in the periodic table, always exhibit -1 oxidation state. Chlorine, bromine and iodine show -1 oxidation state when attached to less electronegative element. They can also exhibit +1 to +7 oxidation states when attached to more electronegative elements like oxygen. These are the few examples where halogens are in positive oxidation states. Rule number 6. This rule is regarding oxidation number of an element in monoatomic ion. The oxidation number of an element in monoatomic ion is equal to the charge on the ion. Suppose we have two ions A N plus and B M minus. Then the oxidation number of element A and B in these ions will respectively be plus N and minus M. For example, in sodium plus, magnesium 2 plus, aluminum 3 plus, chlorine 1 minus and oxygen 2 minus, the oxidation number of sodium, magnesium, aluminum, chlorine and oxygen will respectively be +1, +2, +3, -1 and -2. Rule number 7. In a compound or ion, the more electronegative element is assigned a negative oxidation number, while the less electronegative element is assigned a positive oxidation number. For example, OF2. Here, electronegativity of fluorine is greater than the electronegativity of oxygen. So, fluorine is assigned negative oxidation number and oxygen positive oxidation number. In OCl2, the electronegativity of oxygen is greater than chlorine. Therefore, in this case, chlorine is assigned positive oxidation number and oxygen a negative oxidation number. Rule number 8. This is the last rule, which states that the sum of oxidation numbers of all the atoms in a compound is 0, and in a polyatomic ion it is equal to the charge on the ion. This rule is useful to calculate the oxidation number of an element in a compound or ion. Let's take the example of calculating the oxidation number of sulfur in SF6. We know that the oxidation number of fluorine is -1. Suppose the oxidation number of sulfur is N. Since SF6 is a neutral compound, so we can write N plus 6 into -1 is equal to 0, or N minus 6 is equal to 0, or N is equal to +6. So the oxidation number of sulfur in SF6 is +6. Determination of oxidation number of manganese in KMnO4. Suppose the oxidation number of manganese is N. We already know that potassium always has +1 oxidation number. The oxidation number of oxygen is -2. So we can write +1 plus N plus 4 into -2 is equal to 0, since KMnO4 is a neutral molecule. Or we can write +1 plus N minus 8 is equal to 0, or N minus 7 is equal to 0, or N is equal to +7. Let's take the example of determination of oxidation number of sulfur in sulfate ion. In this case too, we will suppose that the oxidation number of sulfur is N. We know that the oxidation number of oxygen is -2. So we can write N plus 4 into minus 2 is equal to minus 2, since the charge on the sulfate ion is minus 2. Or we can write N minus 8 is equal to minus 2, or N is equal to minus 2 plus 8, or N is equal to plus 6. Now, after learning the rules for the determination of oxidation number, we will do some exercise. Calculation of oxidation number of iron in K2FeO4. Oxidation number of potassium is plus 1. Oxidation number of oxygen is minus 2. Suppose the oxidation number of iron is N. Since this is a neutral molecule, so we can write 2 into plus 1 plus N plus 4 into minus 2 is equal to 0, or 2 plus N minus 8 is equal to 0, or N minus 6 is equal to 0, or N is equal to plus 6. Calculation of oxidation number of carbon in HCN and HNC. We know that the oxidation number of hydrogen is plus 1. The oxidation number of nitrogen is minus 3. Suppose the oxidation number of carbon is N. Since HCN and HNC are neutral molecules, so we can write 1 plus N minus 3 is equal to 0, or N minus 2 is equal to 0, or N is equal to plus 2. Calculation of oxidation number of chromium in sodium chromate. Oxidation number of sodium is plus 1. Oxidation number of chromium is N, and oxidation number of oxygen is minus 2. Since this is a neutral molecule, so we can write 2 into plus 1 plus N plus 4 into minus 2 is equal to 0, or 2 plus N minus 8 is equal to 0, or N minus 6 is equal to 0, or N is equal to plus 6. Calculation of oxidation number of boron in B4O7 2-. Suppose the oxidation number of boron is N. We know that the oxidation number of oxygen is minus 2. So we can write 4 into N plus 7 into minus 2 is equal to minus 2, since there are two negative charges on the ion. We can write 4N minus 14 is equal to minus 2, or 4N is equal to plus 14 minus 2, or 4N is equal to plus 12, or N is equal to plus 12 upon 4, or N is equal to plus 3. Calculation of oxidation number of nickel in NiCO4. Suppose the oxidation number of nickel is N. We know that the overall charge on carbon monoxide ligand is 0. So we can write N plus 4 into 0 is equal to 0, since NiCO4 is a neutral molecule. We can write N plus 0 is equal to 0, or N is equal to 0. Calculation of oxidation number of iron in FeNO3 thrice. Suppose the oxidation number of Fe is N. We know that the overall charge on the nitrate ion is minus 1. So we can write N plus 3 into minus 1 is equal to 0, since the given compound is neutral. Or we can write N minus 3 is equal to 0, or N is equal to plus 3. Calculation of oxidation state of Fe in K4FeCN6. Suppose the oxidation number of Fe is N. We know that the oxidation number of potassium is +1 and the overall charge on the cyanide ion is -1. So we can write 4 into +1 plus n plus 6 into -1 is equal to 0, or 4 plus n minus 6 is equal to 0, or n minus 2 is equal to 0, or n is equal to +2. Calculation of oxidation number of chlorine in HClO4. Suppose the oxidation number of chlorine is n. We know that the oxidation number of hydrogen atom is +1 and that of oxygen is -2. So we can write +1 plus n plus 4 into -2 is equal to 0, or +1 plus n minus 8 is equal to 0, or n minus 7 is equal to 0, or n is equal to +7. Now come to the last section of this lecture, wherein we will be discussing few exceptional examples which are generally asked in competitive examinations. You can solve these questions only when you know the structure of the molecule. Let's take the example of finding oxidation number of carbon atoms in carbon suboxide, which is C3O2. With the knowledge we have based on our discussion in this lecture so far, we can find only average oxidation number of carbon in carbon suboxide and not which carbon is having which oxidation number. Let's first know the average oxidation number of carbon in this molecule. Suppose it is n. As usual, the oxidation number of oxygen is -2. So we can write 3 into n plus 2 into -2 is equal to 0, or 3n minus 4 is equal to 0, or 3n is equal to +4, or n is equal to +4 upon 3. The average oxidation state in fractions suggests that all the carbon atoms are not in the same oxidation state. We can find oxidation number of individual carbon atoms only when we know the structure of this molecule. The structure of C3O2 can be drawn like this. After drawing a structure, we can easily find the oxidation number of any carbon, because the oxidation number of carbon will be equal to the number of bonds through which it is attached to the more electronegative atom, which is oxygen in this case. This carbon is attached to the oxygen atom with 2 covalent bonds. So the oxidation state of this will be +2. Similarly, the oxidation number of this carbon will be +2. The middle carbon, which is attached to 2 carbon atoms, has 0 oxidation number because there is no electronegativity difference between 2 carbon atoms. Thus, in C3O2, there are 2 carbon atoms with +2 oxidation number and 1 with 0 oxidation number. Tribromo octoxide. Let's first find the average oxidation state. In this molecule, suppose the oxidation number of bromine atom is n, and we know that the oxidation number of oxygen is -2. So we can write 3 into n plus 8 into -2 is equal to 0, or 3n minus 16 is equal to 0, or 3n is equal to +16, or n is equal to +16 upon 3. To find the oxidation number of individual bromine atoms, let's draw the structure. This bromine atom is attached to 3 oxygen atoms with 6 covalent bonds. So the oxidation number of this bromine will be +6. Similarly, this bromine atom will also have the oxidation number of +6. This bromine, which is attached to 2 oxygen atoms with 4 covalent bonds, will have the oxidation number of +4. Thus, in B3O8, 2 bromine atoms have +6 oxidation states and one has +4 oxidation state. Sodium tetrathionate. Average oxidation number of sulfur can be calculated as discussed before. Suppose the oxidation number of sulfur is N. Sodium has +1 and oxygen -2 oxidation states. Overall, there is no charge on this molecule. So we can write 2 into +1 plus 4 into N plus 6 into -2 is equal to 0, or +2 plus 4n minus 12 is equal to 0, or 4n minus 10 is equal to 0, or n is equal to +10 upon 4, or n is equal to +2.5. To find the oxidation number of individual sulfur atom, let's draw the structure of sodium tetrathionate. If we look at this sulfur atom, it is bonded to one sulfur atom. Because of this, there will not be any charge on this sulfur atom as both have same electronegativity. As we can see, it is bonded to 3 oxygen atoms with 5 covalent bonds. So, because of this, the oxidation number of this sulfur will be +5. Similarly, the oxidation number of this sulfur will also be +5. If we look at this sulfur, it is bonded to sulfur only. So, the oxidation state of this will be 0. Similarly, this sulfur will also have 0 oxidation state. Thus, in sodium tetrathionate, there are 2 sulfur atoms with +5 oxidation states and 2 with 0 oxidation state. Kairos acid, H2SO5. This is the structure of Kairos acid. If you look at the structure, this is a peroxide bond, and we have already learned that the oxidation number of peroxide oxygen is -1. So the oxidation number of these 2 oxygen atoms will be -1. The rest of the 3 oxygen atoms are normal. So their oxidation state will be -2. If we look at the sulfur, it is attached to 4 oxygen atoms with 6 covalent bonds. So the oxidation number of sulfur in Kairos acid will be +6. Chromium oxide peroxide, CrO5. If you look at the structure, it is having butterfly structure. These 2 bonds are peroxide bonds. So the oxygen atoms connected through this bond will have -1 oxidation number, and the remaining 1 oxygen will have normal oxidation number of -2. If you look at chromium, it is attached to 5 oxygen atoms with 6 covalent bonds. So the oxidation number of chromium will be +6. Now let's discuss the last example of this lecture, which is iron 2,3 oxide, Fe3O4. The structure of this compound can be drawn like this. This iron atom attached to the oxygen with two covalent bonds has +2 oxidation number, while the remaining two, which are attached to oxygen with three covalent bonds, have +3 oxidation state. Thus, in Fe3O4, there is one iron atom with +2 oxidation state and two iron atoms with +3 oxidation state. That's all in this video. Please subscribe my channel and press the bell icon if you like this video. Thank you very much for watching this video.